So I'm going to now do a roughly 30-minute deep dive into FIMS, kind of going into some detail about how this works. I will do a quick introduction of myself. So I spent about 15 years as a consulting engineer, working mainly in New York City, until about 3, almost 4 years ago when I kind of shifted gears and started working on this FIMS technology, and have been working on that ever since. So we'll start by defining FIMS, a centralized mechanical system in which the HVAC distribution and terminal equipment are fully integrated into the building facade such that no components are required within the conditioned space. And we certainly have made this point enough already probably, but the point of this is to make this non-invasive. So this is a mechanical system retrofit that can be installed from the exterior of the building, non-invasively. No components required in the space. Now there are 4 main components of a FIMS system. We have the central equipment, which is generating the heating, cooling, ventilation, and that then gets distributed through duct and pipework that is located outside of the existing facade, but within that new overclad facade, so within a cavity formed between the two. And that's bringing it to the terminal units, which are delivering that conditioning into the space. And then all of that is enclosed within that new outer shell, insulated outer shell around the building. So our talk today, we're going to focus on items 1, 2, and 3, the HVAC piece of this. The facade is certainly extremely important. We could have a whole separate seminar just talking about the facade, but the facade is currently available technology. This is something that's already being done on buildings, and so the new emerging piece of this is what we're doing with the HVAC, and so that's what we'll focus on. We'll start by talking about the central equipment. So it is providing hot water, chilled water, conditioned ventilation air, and exhaust that gets distributed throughout the building. Important thing to note about it is that it's very flexible in terms of the type of central equipment we use. So it's flexible in terms of the source. So this can be conventional electric heat pumps, or it could be something driven by natural gas, renewable natural gas, something like that. It can be air source or water source heat pumps, which means it can connect into a geothermal network or a district thermal network, or you don't even need heat pumps if you have a district thermal network giving you hot and chilled water. It's also flexible in terms of the location of this equipment. So it can be up on the roof like we're showing here. It can be located at intermediate floors in the building. It can be on grade. It can be on a lower level of the building like the cellar. And an important point to make here is you can see that for a relatively large building like this, we're not putting one giant heat pump, one giant air handling unit on the roof. We're actually dividing it into separate building zones. And there's a few reasons for that. One is it minimizes the structural impact with smaller, lighter, distributed equipment. There's less of a visual impact from the street. You end up with smaller duct and pipe mains, and the equipment is smaller, so it becomes easier in terms of maintenance, because at this point we're talking about really light commercial-grade equipment. We're not talking about large, complex heat pumps and air handling units. Now, the duct and pipe distribution is being designed to fit within a narrow cavity between the existing facade and the new facade. And that cavity will mostly be in the 6 to 8 inch range. So the duct and pipe has to fit within that space. So in terms of the duct design, we need to keep the ductwork to a maximum depth of 4 to 6 inches. And then another thing that's very important is to lay it out without any crossovers, because with only 6 inches, there's no way we're going to have any crossovers of the ductwork. We definitely want to design it as a low pressure system because we want to minimize fan energy. And the good thing is, even if it's a rather tall building, when you have a straight run of duct running down the facade without any elbows, fittings, you can actually do it with a very low pressure drop, even when it's a long duct run. And then, of course, we want to be able to balance this at every floor, so using automatic balancing dampers at each branch is probably a good idea. Now, with the piping design, similar considerations. You want it to be low pressure. Again, automatic balancing valves to make sure you're controlling the flow at each floor. It can be designed as a 2-pipe or 4-pipe changeover system. You do want to take freeze protection into consideration. So the piping that's inside of the facade will not be exposed to freezing conditions, but piping on the roof could be. So conventional methods of freeze protection, glycol, antifreeze, or heat tracing, anything like that, would need to be considered. And then again, as with any conventional hydronic system, once you get to taller buildings, you do need to consider zoning it vertically. And that typically happens when you get to buildings in the 15 to 20-story range. Now, the last critical piece of making this system work is the Facade-Integrated Terminal Unit, or the FITU, we'll call it. So you can see it there between the old and new facade. So it's a terminal unit that fits within that narrow space, and it connects to that central ductwork and central piping to deliver the heating and cooling into the space. And it's also mixing in the ventilation air along with the air that it's recirculating within the room. Now, the FITU is a pretty simple unit, only a few main components. So it has a circulation fan, a hydronic coil, and a control valve. And that's essentially it. Now, the trick with it is that it has to be able to fit within a narrow cavity. And once you install it, it's essentially sitting behind the existing wall. And the only way you can access that unit is through that top grill in the windowsill. So all the components need to be designed so that you can access it through the top grill, and the airflow, the supply and the return, has to all be through that top grill. Now, there are a number of benefits to a unit like this. There's only one moving part. It's this small, low-pressure circulation fan. So that means it's very low noise, very low power, and very low maintenance, and very low, or relatively low cost. So now we'll talk a bit about the cavity space. I mentioned typically targeting 6 to 8 inches. Obviously, you want it to be as narrow as possible, but you need to be able to fit your mechanical components. For the most part, if the building's not too big, you can probably keep it at 6 inches. But what's really determining the depth is the ductwork. So if you have a taller building and you need to carry more air in your ductwork, then the ductwork might have to be deeper. So you might have to go more towards 8 inches. And the other thing driving this dimension is the size of the FITU. So if you have a space with higher loads, you might not be able to get that capacity out of a narrow 6-inch unit. You might need to beef it up a little, and that's another thing that can drive you closer to an 8-inch cavity depth. Now, it's important to point out that this cavity is a conditioned space. So the new facade that we're putting on the building is the complete thermal air water vapor barrier now for the building. So this cavity is a conditioned space. There's no freezing risk in there. There's no exposure to outdoor conditions. And one good thing about that is you don't have to insulate the duct and the pipework. But that's something we'll talk a little bit more about later. You do want to consider air movement within this cavity. So you don't want to have airflow due to convection or stack effect. If you have very large continuous cavity outside the building, that could be a problem, as well as fire and smoke spread within that cavity. So you're going to want to break the cavity to stop airflows, fire and smoke flow. Now, the facade performance is extremely important here. Like I said, we're not going to go into too much detail about the facade, but it's important to point out a few things. Fortunately at this conference, it seems everyone is on the same page that, in a cold climate, you can't just throw on heat pumps without improving the facade. So I'm glad I don't have to go too much into that. But having this high performance facade does a lot of really important things for us. Brings down the heat pump size significantly. I mean, we're talking about buildings here that are mostly uninsulated that we're targeting. So you go from an uninsulated building to a highly insulated building. It's a huge reduction in the heat pump system size, which also means a big reduction in electrical upgrades to power those heat pumps. You end up with lower energy bills, so you can actually get some payback on your retrofit. It also improves comfort, and when you're looking at the big picture, it also reduces strain on the electrical grid. So just some kind of basic recommendations would be to meet ASHRAE 90.1 at a minimum for the facade performance, but if you can get to passive house or somewhere close to that, then that's definitely even better. And it's not just about our values and U values. The air tightness is really critical here because we don't want outside air infiltrating into that cavity space. Now, another really important aspect of the facade is the window-to-wall ratio, because if we're running all this mechanical on the outside of the building, we need opaque area to actually run it. So if you have a fully glazed facade, that's going to be a problem. So you need adequate width between the windows to run your risers, and you need adequate height below the windows to actually place your fit-U. So there are some constraints, the maximum glazed area that you can achieve, but you can definitely comfortably get up to 50% glazed area, potentially even more than that. And if you do have a situation like on the bottom of the image here, where say you have ribbon windows, you can block off a portion of those windows in order to run your pipe and ductwork. And if you have that much glazing, it's probably a good thing to block some of it off to be more efficient. Now, we've been talking about multifamily buildings, which also includes hotels and dorms, and it's important to point out why we're targeting that for now. The multifamily buildings have characteristics that are very favorable to this kind of system. So for one, they have shallow floor plates. So if we're conditioning a space completely from the facade, that would be difficult to do if we had deep floor plates. But fortunately, in multifamily buildings, you typically don't have that. They also have low ventilation requirements, that's how we're able to keep the ductwork slim and narrow. And they have relatively low internal heat gains, which is, again, why we're able to condition it with this relatively small, narrow fit-U. So essentially, a multifamily building is skin load dominated, which means when you improve that skin, when you super insulate it, you bring the loads way, way down. And so this is an example on the right of a super insulated building. These are the sensible cooling loads in the space. A typical bedroom might be 800, 1,000 BTUs. Another space with higher loads, like a dining room with a kitchen with some internal gains in there, might be somewhere around 3,000 BTU. But these are very low loads, even lower than typically you can get off-the-shelf equipment for. So looking at this two-bedroom apartment, your total load is only barely over half a ton, and you only need about 45 CFM of ventilation air. So now we're going to do just a quick kind of example design, just so you can see what some of these numbers actually look like when you apply this to a building. And so we'll start by looking at the sizes of the risers. So this example building that we'll be using is a 12-story building. So if we look at a duct that's going from the top to the bottom of the building, serving 12 floors, and we're being conservative here. We're assuming that that duct is supplying 60 CFM of outside air at each floor, which is high, but we're just being conservative. And if we use standard low-pressure ductwork sizing, we end up with a 26 by 5-inch duct and a very low pressure drop on that duct. And then also looking at the pipe, again, being pretty conservative, the amount of GPM that it actually has to supply, and using standard sizing criteria for low pressure pipe, you end up with a 2-inch pipe. Now let's look at the equipment that's going to go up on the roof for this wing of the building. So I mentioned before, each apartment is roughly 0.6 tons. We're serving 24 apartments. That's 2 apartments per floor. And so we get to apply some diversity to that. And so we end up with a roughly 12-ton heat pump to serve this wing of the building. And then the circulation pump circulating the water would be roughly half horsepower. So it's half horsepower to serve 24 apartments. So it's relatively low energy. And then looking at the package ventilation unit, again, being conservative, assuming 100 CFM per apartment, and also assuming we're really cooling that air, really drying it down to a dew point of 48 degrees, which is pretty aggressive. Still, with energy recovery, that'll be a roughly 12-ton unit, and the supply fan power will be 1.5 horsepower. Now, this type of system will definitely not work for every building. As with any type of system, you have to evaluate the building to see if it's suitable, and that definitely applies here. So I already talked about the window-to-wall ratio, and you have to make sure that works. But there's some other things to look for. There's some physical constraints. You just need adequate clearance around the building to be able to install a system like this. If you have a neighboring building that's 5 feet away, then that might not be enough room to do this kind of installation. And you also have to look at the structural capacity of the building to support the extra weight of this external skin. When we're talking about, masonry, steel, concrete buildings like so many of the typical larger multifamilies in New York, the structural capacity typically won't be an issue. But if you start looking at smaller buildings with like a lighter wood frame kind of construction, then you definitely have to take that into account because it might not be able to support it. And then beyond physical constraints, you can have regulatory restraints that might hinder this kind of system. So you might have zoning limitations because we are increasing the volume of the building. We're talking about a roughly 6-inch cavity with a roughly 6-inch insulated facade, so we're increasing the building volume by 12 inches all around, and there could be zoning limitations that prevent you from doing that. Or if you're encroaching on a lot line or a sidewalk, again, that might make growing the building by 12 inches a problem. And then, of course, historic facades. You might not want to cover a historic facade, or you might not be allowed to. Okay, so now we are going to get into some, I'm calling them more advanced concepts. So the first one is actually heating that cavity space. So if you think of insulating the building from the exterior like wrapping it in a blanket, now we'll think of it like wrapping it in a heated blanket. And it's relatively simple to do because we're running the pipework, the piping in that cavity. So if you simply leave that piping uninsulated, then it's going to give off heat into that cavity. That might not be enough heat, so you might want to add some convective elements to get more heat into that cavity, like the element shown in this image below the FITU. Now what this does is we're heating the cavity. That heat will conduct through the uninsulated or poorly insulated existing wall and essentially radiate into the space, creating a radiant wall effect. So obviously a very comfortable way to heat a building, also very efficient because we can do it with very low water temperatures and there's no fan power involved with that. Once you have that heated wall, the only heat loss from the space is through the window. So you just need enough heat from that wall to offset your loss through the window. And this is a new window. It should be a high performance window, so we're not talking about a lot of heat loss here. In most cases, the FITU wouldn't need to run at all in the winter, maybe only on extreme cold days, or if you want to pick up the temperature quickly, like from a setback, then you might need that forced air. But otherwise, for the most part, it won't need to run. And so we're talking about mild temperatures here. We're not talking about very high temperatures. So in this example, we're showing an 80-degree cavity temperature to get that interior wall surface to about 74 degrees, while the space is at 70 degrees. And then what happens when we do this is we create this interesting effect where we're heating that masonry wall. So what we're doing is we're storing heat in that masonry wall. The masonry has a significant amount of thermal mass. So this is essentially free thermal storage. It's also extremely simple and reliable because basically all you have to do is turn the system off, or if the system is lost due to a power outage or something like that, and automatically that wall will just continue to radiate heat into the space. You can even do some interesting things, like if you're anticipating a peak grid event, you could raise your water temperature to push more heat into the wall in advance of that peak event. So there's some interesting things you could do with controls. This is just a very simple calculation here showing that in a 40 square foot wall area of a typical masonry wall construction, if you just increase the temperature of that wall by 4 degrees, that would be enough to maintain temperature in the space for over 6 hours. And of course the reason for that is there's a lot of mass in that wall, and plus it's a super insulated building, so the loads are very low. So now we're going to talk about cooling, because cooling is a little more tricky than heating because we have to worry about humidity as well as sensible loads. And so the way to make this system work is to decouple the sensible from the latent cooling. So at the FITU, we're doing sensible cooling only. We're not forming any condensation. And we're relying on the dehumidified ventilation air to control the humidity in the space. So for those of you who are familiar with chilled beam systems, it essentially operates the same exact way. You can even think of the FITU as like a chilled beam. The only difference is that at least for the way we're designing it, is we're using a fan instead of induction nozzles. But other than that, this is essentially exactly like a chilled beam system. And there are a lot of benefits to this: improved comfort, improved efficiency, and the fact that you just don't need condensate drainage. So when you're doing a retrofit, you don't have to worry about where you're going to route this condensate, how are you going to dispose of it. You save on the cost that you don't have to install a condensate drainage system. And even from a maintenance perspective, you're not worried about cleaning condensate drains or having clogged drain lines. Now, part of making this work requires you to actually supply air into that cavity. So we have this ductwork running in the facade, supplying this conditioned air to the space. So you can take just a little bit of that air and actually supply it directly into the cavity. And that does a few important things for us. It positively pressurizes the cavity to prevent infiltration from outdoors. And it also keeps that cavity nice and dry. And that's how we prevent condensation on those chilled surfaces, those chilled water pipes within the cavity. And then the other thing it does is, the facade should be watertight, but if water does get in there, maybe if you have some kind of extreme rainfall event or something, however water gets in there, you can dry it out relatively quickly because we're constantly supplying this dry air into the cavity. And so that cavity is a relatively small volume. So for a 2-bedroom apartment, with the amount of cavity volume you have, all you would need to do is supply 10 CFM into that cavity to get 2 air changes per hour. So you can get very effective drying and pressurization. Now, the idea here is we're preventing condensation, and so we have to design the system appropriately. And again, this looks very much like a chilled beam system. So the key is maintaining the space dew point below the chilled water supply temperature. And so we're relying on the ventilation air to do that. And so this is a quick calculation showing a 2-bedroom apartment with 5 people. If we're supplying the air at 51-degree dew point, we would actually need about 75 CFM to maintain that humidity in the space. So that's actually more than you require by code. So it's probably your dehumidification that's going to drive your ventilation sizing instead of the code requirement, which in many ways is a good thing because that's good for indoor air quality. It's nice to go above and beyond the code requirement. In this example, I use 51-degree dew point. If you dry it out more than that, you can reduce the amount of air you need. So you can do it with conventional vapor compression cycles, but if you start thinking about using things like desiccants to really dry out that air, then you can really bring down the amount of air that you need. Now, some of you may be thinking, humidity loads are relatively low in an apartment, except you do get these short bursts of humidity sometimes, right? You have hot showers, people cooking, large gatherings, you can have higher humidity loads. So what happens then? The first thing to point out is that if you do get condensate forming, it's going to form on that coil in the FITU. So what's going to happen is it's going to drip into the base of the FITU. So it's not a situation where you're going to have droplets dripping onto your head or onto your computer from the ceiling. So it'll drip into the FITU, and then when that moisture load goes away, it'll quickly dry out because we're supplying that dry ventilation air directly into the FITU. But it is also important to note, I have this reference on the bottom of the slide. It shows that even if your chilled water were to be, say, 6 to 8 degrees below your dew point, which is really losing quite a bit of control over your humidity, even then, after 8.5 hours, you're only barely starting to form droplets. So it's actually not that easy to form these condensation droplets. So in most cases, it really shouldn't be a major concern. But there are things you could do to help prevent it from happening. So one example, you can use a motorized damper on your ventilation air. If you sense high humidity, you just increase the amount of ventilation air. Something else you could do with that is when you sense low humidity, you can reduce your ventilation air. So there's advantages to doing that. You can also do something like just closing the chilled water valve if you sense that humidity is getting too high. So now we'll just take a look at some basic design parameters. So we've shown that we can heat a space effectively with 90-degree Fahrenheit hot water with this system, which is quite good. It means our heat pumps can operate very efficiently. even at very low ambient temperatures. Now the ventilation air supply, we'd want to supply somewhere in the 50 to 70 degree range. I like supplying it at 50 because it means, for one thing, in your rooftop unit you might not need any heating at all because your energy recovery alone might be able to get it up to 50. And the other good thing about it is, I mentioned this can be designed as a 2-pipe or a 4-pipe system. If you design it as a 2-pipe system where you're changing over between heating and cooling, when it's cold out, you can go into heating, but you can still get cooling from that ventilation air when you're supplying it at 50. So it's a way of getting simultaneous heating and cooling capacity even when you have a 2-pipe system. When we look at cooling, again, we have to look at dew points and humidity. So we typically want to control to a roughly 59-degree dew point. Chilled water supply has to be just above that, so 60 degrees. Ventilation air, we want to supply roughly neutral. You don't want to go below 60 degrees again because you might start getting condensation on the surface of the duct. And again, with conventional heat pump equipment, 48 to 52 degrees is a pretty reasonable dew point to use. Now the FITU, with a 6-inch depth, the units that we've built are getting roughly 3,000 BTU, sensible capacity, which, as I showed before, is plenty for most rooms. But if you have, say you have a larger living room, maybe it's a corner unit, you have a lot of windows, so you have a higher load, then you can just use more than one FITU to meet your load. Doing a quick time check. I think we're pretty good. So, okay, so that was getting pretty into the depths of it. Let's step back for a minute and just talk about some of the benefits, why we're doing this. I think we've already emphasized enough the importance of minimizing tenant disruption, but let's look at some of the other benefits, like a dramatic reduction in energy consumption and carbon emissions, because we are super insulating the building, and then we're heating it and cooling it with a heat pump that's operating at very high efficiency. There's big improvements to comfort and indoor air quality. We talked about the thermal storage that we're getting from the existing masonry. Heating and cooling source flexibility, which is allowing us to plug into whatever kind of system makes the most sense on a given site, whether it's geothermal, district network, which I've already mentioned. We're using water instead of refrigerants. I'm sure I don't need to explain the benefits of that and avoiding issues with refrigerants. By having this centralized equipment, we're centralizing maintenance. The only moving part, as I mentioned before, really anywhere in the facade is the small fans in the FITUs, and those will require very little maintenance. So really all the maintenance is being centralized to the equipment that's on the roof. Not just the maintenance, but the noise as well. And you're minimizing your electrical upgrade requirements. So by making the building more efficient, you most likely won't have to upgrade your electrical service, but also in terms of your distribution in the building, the only place that you need to run new power is to that rooftop equipment. You're not running new power to lots of little units all over your building. The power requirement of the fan in the FITU is so small, like in the 20 to 30 watt range, you can even power those with low voltage wiring. A lot of these old masonry buildings actually spend a lot of money maintaining those facades, and once you put this new facade on the building, you can dramatically reduce those maintenance costs. The improvement to acoustics, a big quality of life issue. If you've ever been in a building with bad windows next to like a highway or a train or something like that, this can be a huge quality of life issue for people, but when we insulate it, we reduce the acoustics dramatically. And then just improving the appearance of the building, because this new facade you put on the building can essentially be whatever you want it to be. Whatever materials you want, however you want it to look. So it's a really exciting opportunity to kind of revitalize buildings and neighborhoods from an aesthetic perspective. Okay. Now, if all that sounds great, you're probably still wondering, okay, but how much does it cost? So let's talk about the economics. We're again going to look at one wing of a building. So this is going to be a rough order of magnitude for a system serving 24 apartments. If you look at the cost of the rooftop equipment, the duct and the pipe distribution, and all the FITUs, you would get a total installed cost of about $440,000. When you amortize that over 24 apartments, it's about $18,000 per apartment. which is actually extremely competitive when you compare it to other retrofit solutions on the market, especially when you include ventilation when you're looking at alternatives. But we do think there are opportunities to bring that cost down even further, mainly through prefabricating components. So for example, that rooftop equipment, if you prefabricate it all on a skid and you know, drop it in place, you know, single point of power connection, already wired for controls, everything, you know, there are more opportunities to save cost here. And then we can't just look at the cost alone. We have to look at what are the economic benefits that go along with it. So I already mentioned dramatically reduced energy costs and maintenance costs, which is important. But also when you do this kind of retrofit, you just have a much better building. So things like higher occupancy rates, reducing tenant turnover. If it's a market rate building, the ability to charge higher rents. These can all be big cash flow advantages. And this number, 18,000 per unit, that's not including incentives. There's a lot of incentives out there. So you can imagine once you start applying incentives, just how low that number can get. So it's pretty easy to make the economic case on the HVAC side. The real trick is the facade part. That's the most expensive component here. Now, the facade overclad market is pretty immature right now, and so costs are quite high. The Department of Energy and NYSERDA are really putting a lot of effort, a lot of funding into R&D here to bring those costs down. They're currently targeting getting it down to $15 per square foot of facade area, which if it were to go that low, that would be about $9,000 per two-bedroom apartment. But right now, those costs are actually 5 to 10 times higher than that. So we're a long way from there. Now, again, that's to be expected. This is a new technology. As with any kind of technology, you start out very expensive, but then you kind of ride the cost curve down once you start getting things like economies of scale just from producing these in larger quantities and getting better at it. But then also there's a lot of technology improvement that can happen here. There's a lot of work going into new materials, new, better, more efficient installation methods, all that sort of thing to bring the cost down. But we need it to come down quicker. So policy support needs to be a big part of that, both on the demand side, helping owners to pay for these early projects, and also on the supply side to incentivize manufacturers to really build out that capacity to be able to bring the costs down. So if we were to hit DOE and NYSERDA's target, we would be doing this complete retrofit for under $25,000 per apartment, which again, that's before incentives, and that would be incredibly attractive. But even if we look at the facade cost and say it's triple that, say it's $45 per square foot, we would still be doing these retrofits at about $50,000 total installed cost per apartment, which still works out to be quite attractive economically when you consider the benefits. And again, that's before you take incentives into account.